Welcome to Chapter 9 Practice Problems. There's quite a few of these, and I'm planning on doing this in multiple segments, so this will be segment 1. Without further ado, let's go ahead and get started. Example 9.1. Sport drinks typically contain sucrose, fructose, sodium citrate, potassium citrate, and ascorbic acid, and all the chemical formulas are listed in parentheses, among other ingredients. Classify each of these ingredients as a non-electrolyte, a weak electrolyte, or a strong electrolyte. Try not to peek down at the solution at the bottom, and go ahead and see if you can classify those on your own. If you're stuck, go ahead and take a look at the strategy with me. And just read along. Identify each compound as either ionic or molecular. Ionic, you're looking for a metal and a nonmetal, or a nonmetal polyatomic with a metal, so that you'll have a plus and a minus charge. Molecular is going to be all nonmetals that are covalent type compounds. If it is molecular, identify the molecular compound as acidic, basic, or neither, and identify each acid as strong or weak. So, taking a look at these, sucrose and fructose, they do not contain any metals, no cations, therefore they're molecular. And also, neither is an acid or a base. A lot of times, an acid, for what we'll see, will have a hydrogen written first, some other elements, and then you'll see hydrogens written again. So when the hydrogens are separated, you can say, must be something interesting about this, it's probably acidic. So sucrose and fructose, no cations, therefore molecular. And sodium citrate and potassium citrate, those both contain metal cations, therefore they're ionic. Ascorbic acid, as you can see with the name, is an acid, but also in the formula you can see that a hydrogen is written first. We have H2, C6, and then hydrogens are written again. So there must be something unique about these hydrogens. That uniqueness is that they are acidic hydrogens. And since ascorbic acid does not appear on our strong acid list in Table 9.1, we can assume that it is a weak acid. We pretty much figured out what they would be. Now, if it is ionic, you will be a strong electrolyte. It'll be easy to conduct electricity because of the charges. And if it is molecular, it can either be a non-electrolyte or a weak electrolyte. Sucrose and fructose are non-electrolytes. Sodium citrate and potassium citrate are strong electrolytes because they're ionic. Ascorbic acid is going to be a weak electrolyte. Weak acids and weak bases will both be weak electrolytes, whereas strong acids and strong bases will be strong electrolytes. So hopefully this is fairly straightforward. So let's move on. I'll pause for a moment if you want to read this. Example 9.2. Classify each of the following compounds as soluble or insoluble in water. We have silver nitrate, calcium sulfate, and potassium carbonate. Strategy is we need to make sure that we understand and have the guidelines ready beside us of tables 9.2 and 9.3. And there's a set of rules that we'll need to look for to determine if something is soluble or insoluble. So part A, it does contain a nitrate. Most nitrates are soluble. I mean, pretty much all nitrates are soluble, I should say. Even though silver is usually something that you would see as insoluble, really the only way to get it to be soluble is to pair it up with a nitrate. Part B is insoluble sulfate. Sulfate, when paired with a group 2 ion like calcium, is going to be insoluble. And potassium carbonate, the carbonates are soluble if it's paired with a group 1 ion, as it is here. And just make sure you understand how to read those rules. So think about, check the ions in each compound against the information in both of those tables to confirm that your conclusion makes sense. So again, fairly straightforward, and again, our since our third exam for this course will be take-home, you don't have to memorize these, but if we did have an in-class exam, then if you had a study sheet, you could write these rules on it, and if not, then you would need to memorize the rules. So moving on to example 9.3, write the molecular, ionic, and net ionic equations for the reaction that occurs when aqueous solutions of lead acetate, we get the chemical formula, and calcium chloride are combined. Our strategy here is to predict the products by exchanging ions. This would be like a double replacement reaction. Usually when you have two ionic type compounds, you'll pair the metal cation of one with the non-metal anion of the other metal, or ionic, and then you'll do the non-metal ion of the first with the metal cation of the second, if that makes sense. We'll balance the equation, and then the other thing that we need to do is make sure we have those solubility rules handy, because when we reform a new product, if it is insoluble, then it'll form a solid. Ultimately, we'll rewrite the equation. We're going to show strong electrolytes as ions, and then anything else that are on both sides, we're going to cancel those, and they cancel out, and they're called spectator ions. So let's take a look at all of this visually. The molecular equation, we're given our two reactants. We have lead acetate, which is Pb, C2H3O2, and they could even call this lead 2 acetate, because this would be -1, and there's two of those. Here we have calcium chloride. So we're going to pair together the lead chloride and the calcium acetate. So we want to make sure that when we rewrite our ionic, the charges work. So this is a lead +2, this is a Cl -1. So we need PbCl2 as it's written here. And then for the acetate polyatomic is -1. Calcium is +2. So we need two of the -1 parts so that our charges balance there. So that would be the first part. The second part would be to look at our solubility rules. You're going to see that the acetate with calcium will be soluble, so that will be aqueous. You're going to see that most lead compounds will not be soluble. When it's paired up with an acetate or with a nitrate, it will be in solution, but if it's paired up with a halogen, for example with the chloride, then it is insoluble, so then that would be a solid. So this would be our molecular equation. Our ionic equation is we're going to separate everything that is aqueous that's an ionic compound, and all of these are ionic compounds. You'll separate it off into the ions, and then make sure that we have, if there's more than one, we need to specify. And then if they're on both sides, they cancel. So we can separate lead acetate into the lead +2, and then two parts, because of this 2, acetate. And do the same thing with the calcium chloride, calcium +2, and then two parts of our chloride. This will form lead chloride. Notice how this is not separated. If it's a solid, then you need to leave it together. If it's an aqueous, you can split it up. So this stays together. And then with the calcium acetate, as shown here, we have the calcium +2, and then the two parts of our acetate. And now the lines are drawn through of what's on both sides. So we have two acetates and two acetates. Those cancel out. Those would be spectators. And then with the calcium, you do the same thing. Now we do have lead and chloride on both sides, but since it's in the solid, it's held together, and the ions won't cancel. If we had Pb +2 somewhere on the product side, then of course this one would cancel. Now how this will work is if you have something that is insoluble, you're going to show the ions that came together to form that solid. Everything else cancels out. So our net ionic equation is just going to have what's left over, lead +2, plus 2 parts chloride, forms our lead chloride solid. So this is pulling together multiple ideas. Write this out a few times, make sure you can understand what's going on before you continue. And then one thing to remember is that the charges on the ions in a compound must sum to 0. So make sure you've written the correct formulas for the products that each of the equations you have written is balanced. If you did not write the correct formulas or did not balance correctly, then you'll notice that the ions that are present on both sides won't cancel. And then you can go back and try to figure out what went wrong. Okay. Let's take a look at this fourth example. Milk of magnesia, an over-the-counter laxative, is a mixture of magnesium hydroxide and water. Because magnesium hydroxide is insoluble in water, and you can see that with the solubility rules, the milk of magnesia is a suspension rather than a solution. The undissolved solid is responsible for the milky appearance of the product. When acid, such as hydrochloric acid, is added to the milk of magnesia, the suspended magnesium hydroxide then dissolves, and the result is a clear, colorless solution. Write balanced molecular, ionic, and net ionic equations for this reaction. And we got a nice picture down at the bottom showing the magnesium hydroxide suspension. This looks like a bottle of hydrochloric acid being added. And then we got our clear, colorless solution. So take a moment to go ahead and see if you can do this on your own. If not, then follow along with the strategy and watch the solution. So our strategy for this is to determine the products of the reaction, then write and balance the equation. Remember that one of the reactants is going to be a solid. Identify any strong electrolytes and rewrite the equation, showing strong electrolytes as ions. Identify and cancel the spectator ions. So we start with the magnesium hydroxide as the solid, and then we're going to add hydrochloric acid to it. We wouldn't know that the 2 is there yet, so we would just have MgOH2. Hydroxide is -1, magnesium's +2, so we need 2 hydroxides. HCl, that's H plus, Cl minus. And then this would be quite similar to a double replacement reaction again. So we're going to pair together the magnesium and the chlorine, and then the hydrogen with the hydroxide. When we put together the hydrogen with the hydroxide, we get water. And when we put together the magnesium and the chlorine, we get magnesium chloride. Then you could go back and balance these. You would see that you'd need a 2 in front of HCl and a 2 in front of the water. And putting in the states, or the phase that they are in, the magnesium hydroxide is a solid initially. Hydrochloric acid is all of your acids and bases are going to have some amount of water in it, so it'll be a solution, and that would be aqueous. Water all by itself will not be aqueous because there's nothing else in it. If it's pure, then you would use liquid, and the magnesium chloride would be aqueous. So we can separate these. The magnesium hydroxide, of course, stays together. The HCl will separate into ions. We have 2H plus, 2Cl minus. Notice how the 2 applies to both the hydrogen part and the chlorine part. Pure liquids do not separate, so that would be one thing that is new. So solids don't separate, pure liquids don't separate. So we're going to leave this as H2O. And then we have magnesium chloride. We can separate that into Mg plus 2, and then 2 parts of our chloride. What will cancel out? Well, let's see. We have the chlorines, or the chlorides, here and here, and it looks like everything else will remain. So it says chloride is the only spectator ion, and then our net ionic equation is the magnesium hydroxide plus 2 parts of this proton produces water and magnesium ion. Moving on to the fifth example, determine the oxidation number of each atom in the following compounds and ion. So we have SO2, NaH, CO3 2-, and N2O5. Our strategy for these is for each compound assign an oxidation number, first to the element that appears higher in table 9.5. And make sure you look at table 9.5 and some rules of oxidation numbers before you continue with this. Go ahead and pause and take a look at that if you have it. Then use rule number 2 to determine the oxidation number of the other element. So let's start to take a look at these. In part A, oxygen appears in table 9.5, but sulfur does not. So we assign oxidation number -2 to oxygen. Because there are 2 oxygen atoms in the molecule, the total contribution is going to be double that. So we'll have oxygen is -2. We have 2 of those, so that will be -4. So we figured out the part of the oxygen. Overall, this is neutral. So since it's neutral, then the sulfur must be +4. So what you'll do is you can determine the oxidation number of what you know for sure, and then you can deduce the oxidation number of the other element. All right, so let's take a look at the second one. Once you practice a handful of these, they're fairly straightforward. Both sodium and hydrogen both appear in table 9.5. But since sodium appears higher in the table, we assign the oxidation number to it, which would be +1. So sodium gets the +1. Overall, this is neutral, so what that means is the hydrogen must be -1. So the sodium's +1 and the hydrogen's -1. So let's continue on and look at this third one, which is an ion. Now, the first 2 that we've looked at, we needed to have an overall neutral charge. When you have an ion, you want your overall oxidation numbers to add up to the overall charge of your ion. So this is -2. So oxygen is usually -2, so we assign the oxidation number -2 to oxygen. Because there are 3 oxygen atoms in carbonate, the total contribution will be 3 times -2, which is -6. So this part of the molecule is -6. We need this to be overall -2. So to go from -6 to -2, that means this carbon must be +4. So each individual oxidation number is -2. The carbon is +4. Double check yourself and make sure that your overall would be equal to the charge of your entire molecule. Now let's look at this last one. Oxygen again is -2, so you'll be masters with oxygen, right? And oxygen is very common in these oxidation type situations. We assign the oxidation number -2 to oxygen. Because there are a total of 5, we're going to do 5 times that. So the total contribution would be -10. So that means that this part must be +10, and we have 2 of them, 2 nitrogens, and they'll share that. So then we would take 10 divided by 2 to get 5. So each nitrogen is worth +5. Each oxygen is worth -2. And then again, I mentioned that you should check yourself. And so we'll have 2 nitrogens at +5. That would make this half +10. And then 5 oxygens at -2. That would make this half -10. Now, a lot of times the oxidation number does match the charge of the ion, but not always. So make sure you study a little bit into oxidation numbers. You can probably look up a chart online with a periodic table that shows the common oxidation numbers of various elements. And then here, as the slides have set up, they've used circle and squares. The circle is the individual charge, and then the square is the total charge. And that just separates the 2 ideas from each other. Let's move on to example 9.6. Using the activity series, predict which of the following reactions will occur, and for those that will occur, write the net ionic equation and indicate which element is oxidized and which is reduced. And we have 3 situations to look at. The strategy here is to recognize that the salt in each equation, and that would be the compound on the reactant side, of course, is a strong electrolyte. What is important is the identity of the metal cation in the salt. If the cation appears lower in the table, the solid metal will be oxidized. Therefore, in other words, the reactions will occur. If the cation appears higher in the table, the solid metal will not be oxidized, so no reaction will occur. So one more time is to look at the identity of the metal cation that's in the salt, and if the cation appears lower in the table, then the reaction will occur. And if the cation appears higher in the table, then no reaction will occur. So let's take a look at these. So here we have this platinum chloride. The cation in this is going to be +2. Platinum appears lower in table 9.6 than iron. So here's our formula. We have the iron solid and then the platinum chloride. So if it appears lower, and then look back at this statement, not even write this out if you haven't yet, write this out in your notes. So make sure you understand. So if the cation appears lower in the table, then the solid metal will be oxidized. Therefore, in other words, the reactions will occur. So this will occur. What happens with this and how do we write it? Well, this is what we were given with the iron and the platinum chloride. We're going to take out the chloride part. That's ultimately going to end up as a spectator. And you could write this out in the molecular form and then get down to this form that's at the bottom. This would be like our net ionic. So they've skipped a step here. So here we have iron solid and then our metal cation. And we said that platinum is lower, so therefore this will occur. And what that will do is it'll solidify the platinum, and then we will form iron chloride. And if we look at the overall charges of this, the iron begins, if it's a solid and it's neutral, no charge, it begins at 0. And it goes from 0 to +2. And the platinum is reduced from +2 to 0. The term oxidation, if we look at it with respect to electrons, losing electrons is an oxidation, gaining electrons is a reduction. Sometimes it's hard to wrap our minds around that because when we think of gaining something, we think of adding. But because electrons have a negative charge, when you gain electrons, it becomes more negative. So gaining electrons is reduced. So we go +2 to 0, we can see that's a reduction in charge, but that would gain electrons. This would lose electrons. So let's look at the next two. The cation and this would be gold. Ooh, gold. Gold chloride is +3. Gold appears lower than chromium, so this reaction will occur. Writing out just the net of this, and you could write out the molecular, cancel out, and then write out the net. We have our chromium solid plus our gold cation. That's going to give us our chromium cation and our neutral gold. The chromium will be oxidized, so you'll go from the solid to the charged, and then the gold is reduced. So for these activity series, one other thing that you can see is that when you go from the solid metal to the charged, then you're oxidizing. If you're going from the charged to the neutral, then you are reducing. And that should always be the case until we get into oxidation and reduction type reactions. And let's take a look at this last one. The cation in zinc nitrate is zinc +2. Zinc appears higher in our table than lead. So this is the first one where we've seen the opposite trend. And since it appears higher, then it will not oxidize. You will get no reaction. And so you could either just write NR or no reaction, or just state it as they did here. Therefore, zinc will not oxidize the lead. Check your conclusions by working each problem backward. For part B, for example, write the net ionic equation in reverse, using the same products as reactants. Now compare the positions of gold and chromium. Chromium is higher and cannot oxidize gold. So this confirms your conclusion that the forward reaction will occur and not the reverse. So you could write all of these backwards and then they would occur backwards. That may be confusing, so don't do that if you're understanding this really well. But just to get a better understanding, you could go through that. Okay, so let's continue on to 9.7. Predict which of the following reactions will occur. And for those that will occur, balance the equation and indicate which element is oxidized and which is reduced. And we have three situations here. Our strategy. For part A, the cation in calcium chloride is calcium. Calcium appears higher in the table than aluminum, so since it appears higher, it won't oxidize the aluminum. So that would be no reaction. In part B, the cation in lead acetate is lead 2. Lead appears lower than chromium, so this reaction will occur. The lead plus 2 will oxidize chromium. In part C, the cation in hydroiodic acid is H+. Hydrogen appears lower in the table than tin, so it will oxidize the tin. So for part B, we can separate this off into two half reactions. We can draw it out for the chromium part and for the lead part. I would even write out your initial reaction like we did in the last set of examples here in 9.6. Then we can take this, for example, and split it up into two half reactions. So the chromium with the chromium ion and the gold ion with the neutral gold. So that's what we're doing in this next set. So they went ahead and separated the chromium from the lead from their net reaction. And they have chromium to the chromium ion and then lead to the lead ion to the neutral lead. If you're going from the neutral to a charge and you're going to be oxidized, so this is losing electrons. If you're reduced, you're gaining electrons. When you're oxidized and you're losing electrons, you lose those from this, so they're going to end up on the product side. When you're gaining electrons, they're going to end up on the reactant side. Another way that you can do this without having to really think deeply about it is to match the electrons with the ion. So notice the two reactions. We have the neutral on one side, and then you have your ion and the electrons together on the product side. The lead is going from the charged lead to the neutral lead, and then notice how these electrons are with the lead. The electrons that you gain or going or lose will be equal to the charge. So since this is a +3 charge, this is 3 electrons. Since this is a +2 charge, this is 2 electrons. And the ones we worked in the last example, we didn't have to separate these out, and the electrons matched. They're the same. So you'll notice here that we have 3 and 2, which overall we want to have a conservation, meaning we don't want to have an overall gain or overall loss. Everything needs to balance out. So we need to actually write in molar coefficients. So in order to balance the charges, we must multiply the oxidation half reaction by 2 and the reduction half reaction by 3. Well, why 2 and 3, you may ask? Well, that's because the lowest common denominator is 6. So if we take our chromium part and multiply it by 2 and rewrite it, we get 2 parts of our chromium solid are going to give us 2 chromium 3 ions plus 6 electrons. And then if we multiply our lead part by 3, we get 3 lead ions plus 6 electrons gives us 3 parts of our solid lead. Now if we put these half reactions back together, and how you'll put them back together is take the left side of both reactions and combine it into an overall left side, and take the right side of the reactions and combine it into an overall right side. When we would do this, we would get 2 parts chromium, 3 parts of our lead ion, and then we don't see it, but you're going to notice why in a moment, you'd have your 6 electrons. And then on the right side, we're going to have 2 parts of our chromium ion, 3 parts of our lead solid, and 6 electrons. The 6 electrons cancel on both sides, so you can draw a line through those, and then you'd be left with this as your overall. This would be our net ionic equation. You could work in reverse now, and then give an overall balanced molecular equation, and what you would do is you could just apply back the anionic part that pairs with each of the cations, which is, does it tell us it's acetate? It does. So it tells us it's acetate. So you would just take this acetate, C2H3O2, and put it in both places. And then how many you use would depend on the charge. Since the lead is +2, acetate's -1, we need 2 of them. And since the acetate's -1, the chromium's +3, we need 3 of them. Overall charges here. The chromium's oxidized from and this is just taking the base, 0 to +3, base charge overall, and then +2 to 0. But in reality, we had a change of 6 so that it balanced. So that's pretty tough. If you got that on the first try, then keep going. I would even recommend rewinding a little bit and going back through maybe 1 or 2 more times just to make sure you can wrap your mind around it really well. So it's about 30 minutes right now, and we're maybe about halfway through our worked examples. I'm going to go ahead and stop here, and then we'll have a second part posted up a little bit later. Thank you.